Hello, welcome to this tutorial. I'm Junpeng Lao. I'm currently a data scientist at Google based in Zurich, and I'm also a PyMC dev. So today, I'll walk you through some of the missing value handling in PyMC 3. So everything will be in this collab. Notice that the execution might be out of order because I would be going back and forth a little bit of some of the cells. So if you see out of order execution, please don't be mad. And as for the outline, so I will first walk you through some regression examples. So here simple, meaning that we only have one predictors and an intercept, and everything in terms of the noise is nothing special, Gaussian noise. And we'll see what will happen if we have some missing values in y, so the observations. What would happen if we have missing value in x, and then how would happen if missing value in both, of course. And then go also in the meanwhile some explanation of imputations and how that is done in PyMC 3. And then we'll also look at how that extended to kind of like more than one predictors, like multiple regression. So and how you can do better than just kind of a simple imputations, and to consider into the correlations in the predictor, for example. And last but not least, have maybe some fun in high dimensions. So yeah, right, so let's dive in. Let's start it by generating some data. So here we first assign some fixed parameters to the latent unknown. So we'll have the coefficients, the noise term, and the intercept. And we also generate the predictors. So something sometimes people call a design matrix. And here it's just a vector of an observations drawn from a random from a Gaussian distributions. And we will have our linear predictor here, linear predictions with added some noise. So that's our data x and y plotted here below. We also would generate the missing value or the mass for the missing value. In this case, what I'm doing is that I'm using Bernoulli, so binomial with count, total count is 1, and p 0.1 here, meaning that around 10% would be a missing value. So also show here, so the red dot, they are the missing ones. And now we can see that what will happen if we try to model this. So we'll first generate a new kind of observation now, which is a mass array. And then we'll write down a linear regression model in PyMC 3. So I hope you're all familiar with the syntax of PyMC 3. What we have here is that using a with context, we wrap everything in a meaning that anything is nested under this with context is our model, and we'll assign distributions to all the unknown parameters. So for example, in this case, would be the coefficients, the intercept, and the noise term. And we are assigning a normal to a coefficient and also the intercept, and a half normal to the noise. And then as for the likelihood or what we actually observe, we will add in one more kind of key argument here, which is called y missing. And when you try to execute this, run this cell, you see that the PyMC 3 will give you a warning as listed here. So it says that imputation warning data in the observed contain missing value and will be automatically imputed from the sampling distribution. So what does this mean? We can first look at what are the three parameters in this model. So recall that M0 is our simple regression models. And the three RVs here is a list of all the variables that are unknown. Interestingly, you see that the model added a new kind of unknown that is not specified or not explicitly specified in the model. So what is called is that observe underscore missing. So it's actually the observe here, but added a missing kind of in the name. And Now, anything that in the 3_RVs in this list, they are representing some kind of unknown tensor, and you can think of it as the sampler will see them, meaning that any inference mechanism you're using, has it be MCMC using nuts, or variational inference, or maximum likelihood. Now the model or the inference mechanism or the inference approach, they will know that these are the unknown variables and they will try to inference it. And that's in general how missing value or any arrays that with a mass property is handled in PyMC3. So when you're assigning something that is a mass array to the observed, what PyMC3 does is that it does these imputations. So it might be helpful to go into a little bit more of what imputation means. So here is some simple sketch. So say that you have some data. So here each cell representing one number, and the red one here are the missing values. What imputation does is that it tries to replace these missing values with some kind of numbers. For example, you can use the mean imputations, which usually what people does is that it calculates the column means and then fill that mean into here. But of course, we can do better than this. Using one number is always have a risk that if the number is wrong, it might bias the result quite a lot. So what a more kind of a Bayesian approach to imputation is that instead of assuming one number, we assuming that actually is a distribution. And with a distributions, it's kind of like created representation that we would use a samples usually to represent it. And when we turn the distribution to some kind of MCMC sample, you can think of it as that during the inference or whatever other use case of this missing values, what it does is that each sample is kind of like generate a copy of this data, and these are all kind of like fine. So how does it actually do in PyMC3? What happened is that in PyMC3, you can check the links to the code here. What it does is that whenever there is a mass arrays, it generate a new variables, and then it substitute that into the original observed data. So now it kind of substitute those missing value with this new tensor, and since that now it's a kind of like unknown or tensor in Fiano tensor in the PyMC models, the inference, for example, like MCMC, when it runs, it will try to give it always a numbers during inference. So what it does is that it draw it from the joint distribution or joint posterior, and then it fills in this information. Right, so let's see how it actually behaves when we try to run inference. So here I already run it, and if you look at the trace, so just plot the trace, you see that we have our kind of unknown variables that we will be expecting from linear regression, so the beta, the intercept, and the sigma. But what's interesting here is that now it also fill in the observed values with some distributions. So here, of course, the distribution is represented as some kind of MCMC samples, and you can also check it here that, for example, in this case, we have 9 missing values, so the masked elements, and the posterior also have like 9 of them in the missing value. So which means that you have 9 kind of distribution that fill into this missing value. Now in our initial example here, what we have is that we have the kind of the input. If you think of the input output of a linear regression, we have the input of x and the input of y, and all the missing value are in the y. So in another way of thinking about it, you can consider this as we run a regression, so only on all the fully observed, so no missing data, kind of a subset of the data, and then draw a posterior predicted sample on all those with missing y. So it's kind of the same thing as if you fit the models and then you have some out of sample, or you have a new data set you want to predict and without actual observations. So now you also have the information only in the input but not on the output. So I encourage you to kind of pause the video here a little bit and try to rewrite the above model with no missing value and use the PM sample posterior predicted to infer the missing value and compare with what we have here if you're just using kind of out of the box missing value handling the imputation from PyMC 3. Alright, for the next part, we try to see that what happens if there is missing value in the predictors, and also what happens if they're in predictor n observed. So we do similar thing as above. So we create a mask array of the input as well. And here, again, very similar to the linear regression model above, but now instead of observing on the y underscore missing, we observe on the y directly. And instead of depending on the x, so the predictors, we now depending on x underscore missing. And when you try to run this model, actually it works, which also to my surprise in the beginning. And the reason is that what PyMC 3 does here is that it gets the underlying kind of the mask array stock data, and if the data is not none, or is some value, it actually take that values. So it would actually silently give you the wrong answer or in another word an unintended answer. So what I'm doing here to kind of debug is that I first do coefficient times the y missing with the mask, so that I get the underlying values, and then multiply by PyMC kind of PyMC tensor or a Fiano tensor. And then because since now it's a tensor, if we want to evaluate it, we need to give it a value. So I just give it a 0.01, and you can evaluate kind of any Fiano tensor like this. And turns out that it gives the exact same result if the as the y and the y missing, because it's actually reading the underlying value. So to kind of treat this kind of more properly, we first generate a copy of the predictors and assign every values in the mask, or which are the missing value, as none. And now, as expected, you can see that the model actually doesn't work. So the error message here indicating that there's bad initial energy, which is not surprising because you have some nuns in the predictors, which now kind of like propagated into the likelihood. So what is the proper treatment of doing this? The answer is that instead of putting the x underscore missing directly into the linear formula, we actually assigned it a new variable. So here what I'm doing is that now I assign some prior to the predictors, and I also had it observed to be the y underscore missing. So now it does the imputation magic, that it replaces all the missing value with prior that draw from here, and you can run an inference. What's amazing is that the y missing actually are not drawing from the prior, because now recall that we have a conditional probability here, or the posterior, and since that it conditioned on the data, the information from the observation actually kind of flow back into the predictor here. So any of the missing values now you see, is also drawing from posterior of this full model, so which give you what are the likely distribution of the missing value. So now we are not only knowing that we can kind of like backfill these missing values in a more appropriate ways, and with the informations that kind of borrow from each other. That's also something that I really love about Bayesian statistics, is that we don't ever throw away information in a way. When we model it correctly, all the information kind of like help each other in a way that you can draw the better inference on all your unknowns just because you don't discard any of these informations. And now let's take a step kind of like further to see what would happen if we have both x and so both the predictor and the observer are missing. In this case, the is almost exactly the same as the previous models. The only differences is that we now also observe on the y underscore missing as well. So you can think of it as it has missing value in both x and y. Now after you run inference, you will see there is two kind of missing values from the trait. So you have the x underscore missing, so the missing value in the predictor, and the observer underscore missing. And now since that both of the predictor and observer has no values, what we'll see is that it's just drawing from the priors. Since that we have the x or the predictor be in the prior at 0 and a standard deviation of 3 of a normal distribution, is just drawing from there. And this kind of like no information also propagate into the observer as well. Now that it convoluted with after the linear transformations, it's just kind of like another Gaussian. So you see that for the observer, we also have like no information for all of the missing value. In the next part, we'll see how we can do a little bit better than the model we have currently by adding some hyperpriors to the predictor as well. So by here, what I mean is that recall that in the last example, we have cases like both x and y have no observation, so it's just drawing from some prior. Of course, if your prior is kind of like some fixed prior, it does not give us a lot of information. What we really want is that we are not just drawing from some prior, but we want to kind of get information from the surrounding. Again, something similar as analogies of the mean imputations in the classical sense. So we want to draw it from similar to all the other predictors in the same columns. So here is, let's regenerate some data. And in this case, I also assign a different mask to x and y. So here is the mask. And I'm also making sure that there was some of the masks that they are both missing in x and y. So you can see how that looks like when that happens. And here's what the data looks like. So we have the x missing, y missing, and also this little guy here had both missing. And again, similarly, we generate a missing mask array. And in this case, since that we are modeling them in the observed values, so we don't need to explicitly set in the underlying data to be none for the missing values. And so here is what the model looks like. The differences is that if you recall from before, we have the predictors drawing from a fixed normal prior, but now we assign some hyperparameters or some hyperprior to this distribution. So what it will happen is that it would make an inference on also the mean and standard deviation of the predictors, and then when there was missing value and absolutely no information from others that kind of flows in, it will draw from this like better prior in a way, because now after we do inference, the model should calibrate it to the mean and the standard deviations of the predictors. So just to go back a little bit, to make it kind of like more meaningful, what I have here is that I regenerate a new set of predictors, and here the predictors, they are following a distribution of the mean being 10 and the standard deviation being 2, so that we can compare how the inference result looks like once we fill in the missing values. So we write down our model, we run the inference, and we plot the trace. So we first look at kind of the unknown parameters. And we remember that we have these two values being 10 and 2. And you can look at the distributions. It's definitely kind of covering on the range of the predictors here. Sorry, I mean from the value is as expected on the range. And we also can look at the missing values now from the trace. So we have again each of the x underscore missing being all the missing value from predictors, and observe below, and each is represented as a distributions in samples, in MCMC samples. And we can also observe something quite interesting here, is that most of the distribution, they kind of sharing a very similar shape, but there's two posterior trace here has much wider standard deviations, and intuitively I would suspect that they must be the ones that with both x and y missing. And now you can see that for the x missing that have no information from the observer, it's following a distribution roughly as 10 as the mean and a standard deviation of 2. And we can validate that by plotting it. So what I'm doing below is that I first look at the set of the all the missing values, and now I can select those that have only x missing, only y missing, and both missing. So the figure is plotted here using the Arvis plot posterior. So on the top here are with both x and y missing, and below are some of the kind of random examples that have only y missing, x missing in this one here, and y missing in this one here. So you see that when you have both missing, since there's no information kind of flowing from one way to the other, it actually has a much wider uncertainty, and it's kind of like what we'll be expecting as well. In the next part, we'll look at a multiple regression problem. So I will first look at how it looks like in when we have missing value in a bivariate Gaussian. Again, let's first generate some fake data. Here we will have for generating multivariate Gaussian, we need to specify the mean. So here now is a vector, and a covariance matrix. So the covariance matrix, what we do here is that we will create it using by first specifying correlation matrix, so we know that how the two variables is correlated, and then specify kind of a scale or the standard deviations or the diagonal, the square root of the diagonal of the covariance matrix. And we can combine the correlations and the scale together and make that into the covariance matrix, and to do generate random values from multivariate Gaussian. We can do a Cholesky decomposition of covariance and then do a matrix multiplications, and which I find it the best way to do is using ISM, but there's also other ways to do it, and you can use the NumPy or the SciPy multivariate Gaussian to do the simulations as well. Now we also similarly generate our mass, And after we generate our mask, we now can plot our data. So the data looks a little bit like this. No, a little bit is exactly like this. So the data, we have the missing X, the missing Y, and also there are some both missing. It's not labeled here very clearly. You might already observe that it actually looks quite similar to the linear regressions. It's just that now is instead of modeling as with the input and output and the linear functions, here we are using representing them as a multivariate Gaussian. And I guess in a mathematical sense, they are equivalent in terms that if you have two Gaussian kind of random variable and you rotate them using some kind of rotation matrix, which can be represented as a decomposition of covariance, you have the two kind of equivalence expression of the same thing. Now we can write models, but instead of a linear regression, now we have a multivariate observations. So here is the observations, which is a mass variable as well. And we will put priors on the observations. So we have the mean drawing from a normal, and we also need to specify the covariance or the Cholesky decomposition of the covariance. And in PyMC3, what we usually use is the LKJ Cholesky covariance, and this gives you also new features thanks to Alex. And we can also compute the correlations and covariance and have them stored in the trace as well. And once we run the inference, we can plot the trace. It looks something similar to this. And since the missing value here are in 2 dimensions, you actually see that it's kind of 2 clusters of missing values here. So you have the skinnier ones being from either X or Y, and the kind of shorter one from the other. And we can also plot the correlations or the covariance here. We will be looking at the true free parameters, which are the Cholesky decompositions. And here just has some sanity checks to compare with the true values to see how different they are or how similar they are. And we can also plot kind of the estimated posterior mean compared to the actual missing values. It's not quite exactly lighted on kind of the diagonal straight line, meaning that and you might observe that there is actually kind of a little bit of shift of or what usually people call concentrations towards some kind of mean. And we will kind of explore this phenomenon a little bit more underneath. But at least we have now an example that we can plug in multivariants or multivariant predictors, and we can specify a better prior to capture this linear relationship or the correlations in the predictors as well. So recall that in the previous examples, we try to assign a better priors, so that when there's no information or there's no observations from both X and Y's, you can draw better values from it. And now this idea is really similar in this example, since that we have multi-columns of predictors, and we are assuming that probably each columns has some correlation with one another, and this information shouldn't be kind of lost. So we can use a multivariance priors to capture these relationships across the predictors as well. Because otherwise, what you might do is that you assign just different means and different standard deviation, but the correlation is kind of lost. We can also more formally validate that this actually works. So what I have here is some code to generate conditional for a two-dimension multivariate Gaussian. So here we have the information of the location, scale, and the correlation matrix, and we have the either one of the dimension is observed, so that we then generate a conditional multivariance, and we can have some visualization. Something looks like this. So here you can slice through all the 50 of the missing value and index to each of them. And once you run this code, it shows you what are the posterior looks like, or the sample from a true latent multivariance. And you have the conditional here represented as slicing through this multivariate Gaussians. And you also have the what should be the observation, but now of course is missing. And here on the left, you see that what is the latent truth represented as the dotted line, and the histogram here representing the posterior samples from what we draw using nuts, and also the missing values. And in this case here, the missing value, so we're slicing through x, meaning that the missing value is at x. We can also try to find another index. This is missing in x as well. And here there's an example of missing in y. You see that the posterior samples that we draw using nuts actually overlay quite well with the theoretical kind of correct distribution, conditional distribution. So now we can put everything together and have multiple regressions. So a regression with multiple predictors. Here I regenerate some fake observations with new kind of noise term and intercept, and also generate a new set of masks for the observations. And this is kind of like a full model with multiple predictors and a missing value in both the predictors and the observations. You might remember this part of the code quite similar to above. So I redid the shape from the predictor so that it is a little bit more general. And this part is similar to the linear regression above, just now that the coefficient actually has the shape as the number of predictors you have. And here is also quite similar, differences being that I'm using a matrix multiplications instead of just a simple multiplying a scalar. And then I do the sample from the model and let PyMC3 does its magic. After inference, we can again plot the result, and with the latent true values as a kind of a reference. And yeah, so that would be everything said for in the context of missing value handling. So we have the missing could be in the inputs and the outputs, but all of them now is considered as some kind of outputs that basically assign it to some observed key arguments of distributions. And PyMC3 would build the models and correctly conditions on all the information is variables, and draw and fill in the missing value with some posterior samples so that you can plug it into some other algorithms that you are related on the information related on the predictors or the observed. But now that since the missing value is filled in, you can use those samples to substitute the kind of your initial ignorance of those parameters. As the last part of the tutorial, I want to show you a little bit about what would happen if you have more missing values and how does that impact kind of like the uncertainties. You might have recalled from previously, previous example is that, for example, if you have a two-dimensional Gaussian and both x and y missing, you are drawing from prior. But if your prior has some hyperparameters that is condition on the data, it can actually give better information of how this missing value would be. And in general, I guess it goes without saying that imputations, even by as amazing as PyMC3 is doing, is not one answer for all, meaning that if there's no information, it cannot create this information out of nowhere. So here is some example in higher dimensions, and what I want to demonstrate here is that if what will happen if you have more than one missing values. So for example, what I'm doing here is that I started by generating some random 5-dimensional Gaussian with correlations drawn from Cholesky correlations prior. And here is what the correlation matrix looks like. I wanted to have some high correlation so we can see that how does it reflected in the missing value inference. And I also draw the data here. So here we have the 1,000 observations, and we generate the multivariate normal. Something different to what I did before. Now I use the distribution class from statistical StatsPack submodule from SciPy. And again here I generate some missing values, but the missing value is more systematic, so it shows here. Systematic in a ways that I want to have 5 per type of missing. So the type here we have the missing only 1 dimensions, missing in 2 dimension, 3, 4, until 4. So we have 5 total dimension here. And what we want to see is that when we run the inference, how does the values looks like, or how the posterior sample, whether is close to the actual missing value or not. The model looks something like this. Well, it's still running, but you might see that it's actually quite similar to the 2-dimensional Gaussian. Just now, the only differences is we increase the dimensions, and the prior specification are also put it into quite straightforward. So I will go get a cup of tea and wait for this model to finish running. Alright, so the model finished running. We can plot how the posterior looks like for the missing value. So how the NUS sampler or the MCMC samples fill in these missing values. What I'm doing here is that I select all the missing values index. And you do need to be careful here because in the trace, or how PyMC3 doing now is that it flatten all the missing values. And if you're doing a flatten of some index, it actually goes column wise, and sometimes it could be a bit unintuitive. So make sure that when you are doing indexing, be sure that you are indexing the correct things. And I produce figures like this. So I will skip the code, but feel free to take a look and how I'm actually doing the the index handling. But what I wanted to show here is that we have what happen if we have just 1 missing. So up until 5, column number 5 here, 2 missing, 3 missing, 4 missing, and 5 missing. As you can see, when you only have a few missing, the posterior actually match quite well of what the where the missing value is. So it by borrowing again information from others, condition on the other columns, it actually gives information of how the how uncertain you are with these missing values. And of course, once you have more missing values, the information the model started to become quite uncertain. And then similarly goes goes towards when you have more missing values, it's starting to looks like just drawing from the prior. Something interesting that I sometimes observe here is that when you have a lot of missing values, I feel like the posterior tend to kind of concentrate it more towards the mean, kind of a little bit like regression to the mean. Of course, I have not formally verified it. It'll be interesting to see whether that is actually the case. But in general, I guess the take-home message here is that imputation is great and it should work quite well. But when you have a lot of missing values, the imputation also is not a magical method that can fix everything. And once you have the data quality is not good and lots of missings, it's always better just to go out and collect better data. So that's all for today for this tutorial here. There was a few additional informations that if you like, encourage you to take a look. For example, I have this blog post on how to do outsample prediction for linear model with missing data. It's from a pretty long time ago, but the idea still stands. And there was also some discussion on the PyMC discourse about how do you marginalize or condition on the multivariate normal. And I find that those discussions are quite helpful. And there's also, I find this course notes is in R, but it covers quite good information of, in general, how do you handle missing data. And I would love to see some of those packages translate into Python and in PyMC 3 as well. So hope you enjoy this tutorial and hope you come up with a better knowledge of how you can do missing value handling in PyMC 3. And as always, if you have questions, feel free to reach out to me and post your questions on Discourse. See you!